October 26, 1940. Mines Field, California. Edgar Schmood watched the North American Aviation NA-73X prototype taxi toward the runway for its maiden flight. The aircraft's distinctive ventral scoop hung beneath the fuselage like an afterthought, a bulbous appendage that test pilots had already dubbed useless drag. Saibo, within minutes, that supposedly inefficient Radiator design would prove its critics wrong and transform the P-51 Mustang into the most successful long-range fighter of World War II. Schmood had created something unprecedented, a cooling system that defied conventional wisdom and turned waste heat into jet thrust. What Schmood had accomplished violated every principle of aircraft design taught in engineering schools. Radiators were supposed to create drag, not eliminate it. Cooling systems were necessary evils that reduced performance in exchange for engine reliability. Yet the German immigrants' radical approach to the Meredith effect would make the Mustang faster than fighters designed specifically for speed. His useless radiator shape would become the foundation for jet-age design principles and establish North American aviation as a leader in high-performance aircraft development. The story of how Edgar Schmood's Radiator design transformed the P-51 into a jet-age legend doesn't begin with aerodynamic innovation. It begins with immigration, self-education, and an aviation industry that dismissed unconventional approaches to fundamental engineering problems. To understand why Schmood's ventral scoop represented such a radical departure from accepted practice, you must first understand how aircraft cooling systems were designed in 1940, and why the aviation establishment believed his approach would fail. When Edgar Schmood joined North American Aviation in 1936, aircraft radiator design followed rigid conventions established during World War I. Liquid-cooled engines required large radiators that disrupted airflow and created substantial drag penalties. Designers minimized these penalties by hiding radiators behind propellers, mounting them inside wings, or placing them where they would cause the least aerodynamic interference. The fundamental assumption was that cooling systems necessarily reduced aircraft performance. The conventional wisdom had sound theoretical basis. Any object placed in an airstream creates drag by disturbing the smooth flow of air around the aircraft. Radiators, with their complex internal structures and required ducting, created particularly severe drag penalties. Wind tunnel tests consistently showed that cooling systems could account for 15 to 25% of total aircraft drag. Designers accepted these penalties as unavoidable consequences of liquid-cooled engines. Edgar Schmood seemed an unlikely candidate to challenge fundamental aerodynamic principles. Born September 10, 1889 in Heilbronn, Germany, he came from a working-class family with no engineering background. His father was a master baker. His mother managed the family bakery. Schmood left school at 14 to apprentice in a machine shop, where he learned practical engineering through hands-on experience rather than formal education. During World War I, Schmood served as a mechanic with the Austro-Hungarian aviation troops, maintaining and repairing military aircraft. The experience introduced him to aircraft design and sparked an interest in aerodynamics that would define his career. After the war, economic devastation in Germany motivated Schmood to emigrate to Brazil in 1925, where he found employment with General Motors' aviation division in São Paulo. Schmood's Brazilian experience proved crucial to his later success. Working for General Motors exposed him to American engineering methods and mass production techniques. More importantly, it provided the sponsorship necessary for immigration to the United States during the restrictive quota system of the 1920s. In 1931, Schmood became one of only 794 people admitted under the Austrian quota and went directly to work for Fokker Aircraft Corporation of America in New Jersey. The Fokker experience introduced Schmood to cutting-edge aircraft design methods. As a preliminary design engineer, he learned to integrate propulsion, aerodynamics, and structural requirements into unified aircraft concepts. When General Motors sold its aviation assets and Fokker became part of North American Aviation, Schmood moved to the new company's facilities in Maryland and later to Los Angeles, when the operation relocated in 1935. At North American Aviation, Schmood worked under James Kindleberger, a visionary leader who encouraged innovative approaches to aircraft design problems. Kindleberger recognized Schmood's practical engineering skills and promoted him to Chief of Preliminary Design. The position gave Schmood authority to explore unconventional solutions to aerodynamic challenges that conventional engineering approaches could not solve. Schmood's opportunity came in April 1940, when the British Purchasing Commission approached North American Aviation about producing Curtiss P-40 fighters under license. Instead of accepting the contract for an obsolete design, Kindleberger proposed building a superior fighter from scratch. The British agreed to fund development of a new aircraft that would incorporate the latest aerodynamic innovations and provide better performance than any existing fighter. The challenge was enormous. North American had never designed a high-performance fighter aircraft. The company's experience was limited to trainers and medium bombers. The British contract required delivery of a prototype within 120 days, an impossibly short timeline for conventional aircraft development. Schmood would have to innovate not just in design, but in development methods to meet the deadline. Schmood's team included Raymond Rice, the chief engineer, and Lee Atwood, assistant general manager for technical affairs. The group represented diverse backgrounds and approaches to aircraft design. Rice brought theoretical knowledge and wind tunnel experience. Atwood contributed project management skills and understanding of production requirements. Schmood provided practical engineering insight and willingness to challenge conventional assumptions about aircraft design. The Radiator problem emerged early in the design process. The British specified the Allison V1710 engine, a liquid-cooled power plant that required substantial cooling capacity. Conventional Radiator installations would create significant drag penalties that would compromise the aircraft's performance. Schmood needed an approach that would provide adequate cooling without destroying the aerodynamic efficiency essential for a superior fighter. Schmood's solution drew inspiration from theoretical work published by British scientist F.W. Meredith in 1936. Meredith had proposed that properly designed cooling ducts could recover waste heat and convert it into useful thrust. The concept involved compressing incoming air, heating it as it passed through the radiator, and accelerating it through a carefully shaped exit duct. Under ideal conditions, the resulting thrust could offset or even exceed the drag created by the cooling system. The Meredith effect represented a revolutionary approach to aircraft cooling that challenged fundamental assumptions about radiator design. Instead of hiding cooling systems to minimize drag, Meredith proposed designing them to produce thrust. The concept required sophisticated understanding of thermodynamics and fluid mechanics that few aircraft designers possessed. Most engineers dismissed the theory as impractical for operational aircraft. Schmood believed the Meredith effect could be implemented successfully if the cooling duct was designed with sufficient attention to aerodynamic detail. His approach involved creating a ventral scoop that would compress incoming air, distribute it evenly across the radiator matrix, and accelerate it through a convergent exit nozzle. The entire system would be carefully shaped to maintain attached airflow and minimize turbulence. The ventral placement was controversial. Conventional wisdom suggested that radiators should be positioned where they would not interfere with critical airflow around wings and control surfaces. Schmood's design placed a large scoop directly beneath the fuselage, where it would be prominently visible and potentially disruptive to aerodynamic flow. Critics argued that the placement would create more drag than any theoretical thrust could overcome. Schmood's calculations suggested otherwise. The ventral position offered several advantages over conventional installations. The scoop could take advantage of high-pressure air beneath the fuselage without disrupting low-pressure flow over the wings. The long duct provided space for proper diffusion and compression of incoming air. Most importantly, the design allowed precise control of airflow through the radiator matrix and exit nozzle. The detailed design of the cooling system required innovations in multiple areas. Schmood developed a compound curved inlet that would compress incoming air while maintaining attached flow. The diffuser section gradually reduced air velocity to optimize heat transfer through the radiator. The exit nozzle was carefully shaped to accelerate heated air and convert thermal energy into forward thrust. Construction of the cooling system presented unprecedented challenges. The complex curves of the inlet required hand-forming techniques that had never been used in aircraft production. The ducting demanded precise tolerances to maintain the pressure differentials necessary for proper operation. Quality control procedures had to be developed to ensure consistent performance across multiple aircraft. Wind tunnel testing at the California Institute of Technology confirmed Schmood's theoretical predictions. The cooling system produced measurably less drag than conventional installations while providing superior cooling capacity. Under certain flight conditions, the system actually generated net thrust that added to the aircraft's performance. The tests validated the Meredith effect as a practical engineering solution rather than theoretical curiosity. The NA-73X prototype first flew on October 26, 1940, just 102 days after contract signing. Test pilot Vance Breese reported exceptional handling qualities and performance that exceeded expectations. The aircraft demonstrated speeds comparable to fighters designed specifically for speed, while carrying the fuel capacity necessary for long-range missions. The ventral scoop had not compromised performance as critics predicted. The compressed development timeline had forced Schmood's team to employ unprecedented design and manufacturing techniques. Traditional aircraft development involved years of iterative design, testing, and refinement. The British contract allowed only months to complete an entirely new fighter design. Schmood addressed this challenge by developing mathematical modeling techniques that could predict aerodynamic performance without extensive wind tunnel testing. The mathematical approach represented a revolutionary departure from conventional aircraft design methods. Previous designs relied heavily on empirical data gathered from similar aircraft and extensive model testing. Schmood's team used conic sections to define the fuselage shape, creating smooth curves that could be calculated precisely rather than approximated through trial and error. This mathematical precision enabled rapid manufacturing while ensuring optimal aerodynamic performance. The manufacturing challenges were equally demanding. The complex curves of the radiator inlet required precision forming techniques that pushed the limits of available metalworking technology. Sheet metal workers had to hand-form compound curves without the benefit of modern computer-controlled machinery. Quality control procedures were developed specifically for the Mustang program to ensure consistent performance across multiple aircraft. The cooling system integration demanded coordination between multiple engineering disciplines. Aerodynamicists designed the external shape for optimal airflow. Thermodynamics specialists calculated heat transfer rates and temperature distributions. Structural engineers ensured that the installation could withstand combat loads and operational stresses. The collaborative approach established new standards for integrated design methodology. Testing of the cooling system began before the complete aircraft was assembled. Individual components were evaluated using specialized test equipment that simulated operational conditions. The radiator matrix was tested for pressure drop and heat transfer efficiency. The inlet and exit ducting were evaluated for flow characteristics and pressure recovery. These component tests validated design calculations and identified potential problems before first flight. Initial flight testing revealed the full potential of Schmood's cooling system design. The Mustang achieved cruise speeds of over 300 miles per hour while maintaining engine temperatures well within acceptable limits. The cooling system operated efficiently across a wide range of flight conditions without requiring complex control systems or pilot intervention. Most remarkably, fuel consumption was lower than anticipated, suggesting that the cooling system was indeed contributing thrust rather than creating drag. The Royal Air Force quickly recognized the Mustang's exceptional capabilities and ordered large quantities for operational use. Early combat reports confirmed that the aircraft's performance advantages translated into tactical superiority over German fighters. The combination of speed, range, and maneuverability made the Mustang ideal for escort missions that existing fighters could not accomplish effectively. The Mustang's success attracted attention from American military leaders who had initially shown little interest in the design. Army Air Force's testing confirmed British reports about the aircraft's exceptional performance. When the decision was made to develop a Merlin-powered variant, Schmud's cooling system required only minor modifications to accommodate the more powerful engine. The basic design proved adaptable to different power plants and mission requirements. The P-51B and subsequent variants incorporated refinements to Schmud's original cooling system design. The larger Merlin engine required increased cooling capacity that was achieved by enlarging the radiator matrix and optimizing the ducting geometry. Despite these changes, the fundamental principles remained unchanged. The ventral scoop continued to provide efficient cooling, while contributing thrust to overall aircraft performance. Combat operations in Europe validated Schmud's innovative approach under the most demanding conditions. P-51 pilots reported exceptional reliability and performance during long-range escort missions to targets deep in German territory. The cooling system operated effectively even when aircraft sustained battle damage that would have disabled conventional installations. The robust design provided redundancy and fault tolerance that proved essential in combat operations. The operational testing revealed unexpected benefits of Schmud's design approach. Pilots discovered that the Mustang's cooling system responded rapidly to changing flight conditions without requiring manual intervention. The carefully designed ducting maintained optimal engine temperatures across a wide range of speeds and altitudes. This automatic regulation reduced pilot workload during critical combat phases and improved overall mission effectiveness. Battle damage assessments provided crucial validation of the cooling system's robustness. German fighter pilots specifically targeted the ventral scoop, believing it to be a vulnerable point in the Mustang's design. However, the large internal volume and multiple flow paths provided significant redundancy. Aircraft with substantial damage to the cooling system could often complete their missions and return to base safely. The maintenance advantages became apparent as the war progressed. Ground crews found that Schmud's design allowed easy access to cooling system components for routine maintenance and battle damage repair. The modular construction enabled replacement of damaged sections without extensive aircraft disassembly. These practical considerations proved crucial for maintaining high operational availability rates in forward deployment conditions. Intelligence reports indicated that German engineers had studied captured Mustangs extensively, attempting to understand the principles behind the superior cooling system performance. Several German aircraft designs incorporated modified versions of Schmud's concepts, though none achieved comparable integration and effectiveness. The attempted copies validated the sophistication of the original design, while demonstrating the difficulty of replicating complex aerodynamic systems. Post-war analysis revealed the full extent of Schmud's achievement. Detailed testing showed that the Mustang's cooling system reduced total aircraft drag by approximately 30% compared to conventional installations. Under optimal conditions, the system produced net thrust equivalent to about 300 pounds of force. The performance gains enabled mission capabilities that would have been impossible with traditional cooling systems. The implications extended far beyond the P-51 program. Schmud's successful implementation of the Meredith effect influenced cooling system design for subsequent aircraft projects. The principles were incorporated into jet engine installations, where the concept of using waste heat to produce thrust became fundamental to propulsion system efficiency. Modern aircraft cooling systems continue to employ techniques pioneered in the Mustang design. Schmud's achievement also demonstrated the value of challenging conventional engineering assumptions. His willingness to pursue unconventional solutions led to breakthrough innovations that established new paradigms for aircraft design. The success encouraged other engineers to explore theoretical concepts that might have practical applications, despite skepticism from established authorities. After the war, Schmud continued developing advanced aircraft designs at North American Aviation. His work on the F-86 Sabre, incorporated lessons learned from the Mustang program, and established North American as a leader in jet fighter development. The P-51's success provided the foundation for the company's dominance in military aircraft design throughout the Cold War period. The transition from propeller-driven to jet aircraft presented new challenges that drew heavily on Schmood's cooling system expertise. Jet engines operated at much higher temperatures than piston engines, requiring more sophisticated cooling approaches. The principles of integrated heat management and thrust recovery that Schmood had pioneered with the Mustang became fundamental to jet engine installation design. The F-86 Sabre demonstrated direct application of Mustang design principles to jet fighter requirements. Schmood's team developed air intake systems that compressed incoming air for the turbojet engine while maintaining the smooth airflow characteristics essential for high-speed flight. The integration between propulsion and aerodynamic systems followed methodologies established during the Mustang program. The F-100 Super Sabre pushed these concepts even further, incorporating supersonic design requirements that demanded precise understanding of high-speed airflow management. Schmood's mathematical modeling techniques, originally developed for the Mustang's complex curves, proved essential for defining aircraft shapes that could operate efficiently across subsonic and supersonic speed ranges. Corporate recognition of Schmood's contributions led to his appointment as North American's chief designer for advanced projects. This position allowed him to influence multiple aircraft programs simultaneously, ensuring that the integrated design philosophy pioneered with the Mustang became standard practice throughout the company. The systematic approach to design optimization established North American as the premier developer of high-performance military aircraft. The Korean War provided operational validation of Schmood's jet-age designs. F-86 pilots reported exceptional performance characteristics that directly descended from innovations first implemented in the Mustang cooling system. The ability to maintain optimal engine performance across varying operational conditions proved crucial for air superiority missions against advanced Soviet-designed fighters. In 1952, Schmood left North American to join Northrop Corporation as Vice President of Engineering. His new position allowed him to apply Mustang design principles to different types of aircraft. The F-5 Freedom Fighter incorporated refined versions of techniques pioneered in the P-51 program. The success of the F-5 validated Schmood's design philosophy across multiple aircraft categories. The recognition came gradually for Schmood. The aviation industry initially credited the Mustang's success to superior manufacturing and materials, rather than acknowledging his specific design innovations. Only after detailed post-war analysis did engineers fully understand the sophisticated aerodynamics that made the aircraft so successful. Schmood's contributions were finally recognized as fundamental to the aircraft's legendary performance. Modern computational fluid dynamics has validated Schmood's intuitive understanding of complex aerodynamic phenomena. Computer modeling confirms that his cooling system design achieved optimal pressure distributions and airflow patterns without the analytical tools available to contemporary engineers. The achievement demonstrates exceptional engineering insight and practical problem-solving ability. 21st-century analysis using supercomputer simulations has revealed the full sophistication of Schmood's original design. The ventral scoop creates a complex three-dimensional flow field that maximizes pressure recovery while minimizing turbulence and separation. Modern engineers, despite having access to advanced computational tools, struggle to improve upon the basic configuration that Schmood developed using only wind tunnel data and mathematical intuition. The precision of Schmood's calculations has impressed contemporary aerodynamics researchers. His estimates of pressure distributions, flow velocities, and thrust production have proven remarkably accurate when compared to modern computational results. The achievement is particularly notable, given that Schmood accomplished this analysis using slide rules and mechanical calculators rather than digital computers. University research programs studying historical aircraft design consistently identify the Mustang's cooling system as a breakthrough achievement in applied aerodynamics. Graduate students analyze the design as an example of successful integration between theoretical knowledge and practical engineering constraints. The case study demonstrates how innovative thinking can produce solutions that exceed the performance of conventional approaches. NASA research into advanced aircraft concepts has revisited Schmidt's Meredith effect implementation as a potential model for future designs. Spaceplane configurations and hypersonic vehicles could benefit from integrated cooling and propulsion systems that recover waste heat for useful thrust production. The principles Schmidt established continue to influence cutting-edge aerospace research programs. The restoration community has provided additional validation of Schmidt's design excellence. Engineers working on P-51 restoration projects consistently report that the cooling system components demonstrate exceptional precision and attention to aerodynamic detail. Original manufacturing drawings reveal sophisticated understanding of fluid mechanics that rivals modern design practices. The legacy of Schmidt's Radiator design extends beyond aviation to other engineering disciplines. The principles of using waste heat to produce useful work have been applied to automotive design, industrial processes, and space exploration systems. The Mustang's cooling system established precedents for integrated design approaches that optimize multiple functions within single systems. Racing aircraft continue to employ refined versions of Schmidt's cooling system concepts. Modified P-51s competing at the Reno Air Races achieve speeds exceeding 500 miles per hour, using enhanced versions of the original Meredith effect design. The performance demonstrates the enduring validity of principles Schmidt established over 8 decades ago. Contemporary aircraft designers study the Mustang's cooling system as an example of successful integration between theoretical innovation and practical engineering. The design achieved performance improvements that seemed impossible according to conventional wisdom, while maintaining the reliability and manufacturability necessary for operational aircraft. The achievement represents a perfect balance between innovation and pragmatism. Edgar Schmid worked at North American Aviation for 22 years, designing aircraft that shaped the development of military aviation throughout the jet age. His most famous creation, the P-51 Mustang, demonstrated that unconventional approaches to fundamental engineering problems could produce revolutionary improvements in aircraft performance. The ventral radiator scoop that critics dismissed as useless drag became the key to the aircraft's exceptional capabilities. On October 26, 1940, at Mines Field, California, the NA-73X prototype demonstrated that Schmidt's radical cooling system design worked exactly as intended. The supposedly inefficient radiator installation helped make the Mustang the most successful long-range fighter of World War II. The German immigrants' innovative application of the Meredith effect established principles that continue influencing aircraft design 8 decades later. Schmidt's story represents more than individual achievement or technical innovation. It demonstrates how challenging established assumptions can lead to breakthrough discoveries when supported by rigorous analysis and practical engineering skill. The young apprentice who became one of aviation's most influential designers proved that innovation often emerges from willingness to pursue unconventional solutions to conventional problems. That's how Edgar Schmidt's useless radiator shape turned the P-51 into a jet-age legend through aerodynamic innovation that validated theoretical principles, established new design paradigms, and influenced aircraft development for generations beyond his own.